In this video, I'm going to tell you about PU learning, which stands for Learning from Positive and Unlabeled Data. I'm also going to try to convey why this is such an important problem by discussing the different sources from which this kind of data can originate. Okay, let's get started. Learning from positive and unlabeled data is actually binary classification, but only the data that we're going to use looks a bit different than usual. So let's look at just normal binary classification first. This example is about loan applications. The blue applications are applications that qualify for getting a loan, whereas the red ones are applications that do not qualify for a loan. From this data, where we have these examples of applications that qualified and applications that did not qualify, the aim of binary classification is to learn a classifier that can find this decision boundary here. The decision boundary distinguishes the positive from the negative examples. In binary classification, we assumed that we had these positive and negative examples, that all the examples had a label positive or negative. The difference in positive and unlabeled data, or PU data, is that we do not have all of these labels. So instead of knowing for all of the examples if they're positive or negative, only a subset of the positive examples actually do get these labels. The rest of the examples are unlabeled. So an example that gets a label will always be positive because only positive examples get labeled, but unlabeled examples can be both negative or positive. Now that the colors which indicated the true class labels disappeared, it's much less clear how to find the decision boundary. So one way to draw it would be like this, because then we include all of the positively labeled examples on one side. So we say, yeah, probably that will be the positive class. However, we could also say, now because it's less clear how to choose it, let's do something more simple and just split on one feature. So let's split on feature B. And then we have almost all of the examples on the right side of this boundary. Or we could go even more conservative and just say like, okay, here there's a clear cluster. So let's just take those as positive and predict everything else as negative, just because we don't know. So this is the challenge of learning from positive and unlabeled data, still finding the decision boundary even though we have much fewer labels and only from one class. So why would you be interested in PU learning when just binary classification is so much easier? Well, as you might guess, this kind of data, the PU data, actually naturally arises in many applications. And to convince you of this, or to just give you an idea of what this kind of applications might be, I'll give you a list of 10 sources of this kind of data. As a disclaimer, this is not a complete list of sources, it are just sources that appeared that were described in several papers, and also some of the sources may overlap, which means that one specific application could be described as multiple sources of this list. Okay, let's get started. Source number 1, automatic diagnosis. An automatic diagnosis system aims to predict if a patient has a disease or not. The data for such a system would consist of, on the one hand, patients that actually were diagnosed with this disease, and on the other hand, patients that were not. However, not being diagnosed with a disease is not the same as not having the disease. Actually, many diseases, like diabetes, often go undiagnosed. Therefore, it's safer to regard the patients that were not diagnosed as unlabeled and just the diagnosed patients as positive. Source number 2. Positive examples are easier to obtain. This is typically the case in recommendation systems. Think, for example, about this online fashion retailer. It might want to recommend articles of interest to its potential buyers. To learn what an article of interest is, we can check what the buyer has been looking at. So this would be positive examples. Here in this case, we can see from the positive example that this buyer might be interested in elegant female shoes. But what are the negative examples? Can we just take all of the other items of the website? Well, probably not, because exactly these are the items that you would like to recommend, things that she hasn't yet looked at but might still be interested in. It also doesn't make sense to ask the user to point out some negative examples to us. Therefore, all the other items are unlabeled and just the items that she has watched are positive examples. Source number 3, indirect labels. In this case, we actually have no labels about the class at all. But we might have other features which do indicate that the class is positive. So we can just use these features as indirect labels. Imagine, for example, that we want to predict in our student population of our university which students are active, as in which students do sports and which ones do not. To obtain this information, we could ask a subsample of the students about their habits, but there might be an easier way. We can look at which students do have sports subscriptions of the university itself. For example, I do have a sports card, but Jesse, on the other hand, he doesn't have a sports card. Can we then conclude that Jesse is not active? Well, definitely not. So we can only say that students who have a sports card are active and students who do not have a sports card are unlabeled. Source number 4, case control. In the case control scenario, we actually train a model using two datasets. On the one hand, we have the case dataset, which represents the population of interest. So for us, this would be the population of positive examples. On the other hand, there is a control dataset, which represents the general population. So, for example, if you would like to predict the socioeconomic status of patients from their health records, we could gather positive examples from the hospitals that are in an upper class neighborhood. These look like castles because everybody there is super rich. The general population could then be represented by health records that come from hospitals from all over the country, not discriminating which neighborhoods they are from. These will thus be the positive examples, and the general population is considered as unlabeled. Source number 5, negative class data shift. This occurs when the distribution of the negative example changes while the positive distribution remains the same. This happens, for example, in adversarial scenarios like spam filtering. In spam filtering, we might want to train a spam filter based on a positive, so good emails, and negative examples, hence spam. When training the model, the positive examples will lie in one part of the space and the negative examples in another part of the space. The training process will then learn the decision boundary between the two classes. Unfortunately, once the spam filter exists, the negative class, the spammers will shift their style so that they still become inside the decision boundary, on the right side of the decision boundary. And then, of course, we would have to train a new model. It would be very painful to every time label new negative examples. Therefore, in this case, it might be easier to just use PU learning and each time just take a representative sample from the entire distribution as unlabeled examples and just keep the same positive examples from before as the labeled positive ones. Source number 6, underreporting. In surveys, underreporting occurs when participants are likely to give false negative responses. This typically occurs for issues that have social stigma, such as maternal smoking. So take for example this lady. She's pregnant and she was meaning to give up smoking, but she couldn't. So if she is then asked in a survey if she smokes or not, she's very likely to lie just because she feels guilty. This kind of underreporting actually occurs quite often. Gorber et al. Have even shown that smoking may be underestimated by up to 47%. In this setting, a negative response is really just an unlabeled example, because it's not because you say that you're not smoking that you actually don't do it. However, a positive response is definitely a positive example. Source number 7, one-class classification. The goal of one-class classification is to recognize examples from the class of interest. We would call this a positive class, from the entire population. So here we would want to find this class. When unlabeled examples of the entire population are available, then this can be seen as learning from positive and unlabeled data. In this case, the negative class often has a large variety for which it could be difficult to label a representative subsample. Take, for example, the task of classifying certain areas in satellite pictures. For example, the class of interest could be houses or roads or grass areas. If you have the class of interest in mind, it's not that hard to find examples, but it is hard to find negative examples because those are just too diverse. Source number 8, Inlier-based outlier detection. Outlier detection aims to find unexpected examples in a dataset. This is, for example, used quite often to monitor the health of industrial machines using sensors. If suddenly the machine starts to make a different sound, then probably something is up. This is usually done just with unsupervised data. Inlier-based outlier detection, on the other hand, has, in addition to the unsupervised data, access to a representative sample of inliers. So this would be examples of machines in good conditions. With this information, more powerful outlier detection is possible, as was shown by Hido and Smola. This task can of course be phrased as PU learning, with the inliers as examples of the positive class and the unsupervised datasets as the unlabeled examples. This was first shown by Blanchard et al. Source number 9, knowledge base completion. Knowledge bases are used to organize knowledge, which can then be retrieved in a structured way. The Google Knowledge Graph, for example, is used to compose the knowledge panels that are shown when you search for famous people. The knowledge panel is generated from the knowledge graph, which looks like this. It consists of entities like people or universities or papers that are related to each other, that are connected through relations like here I am affiliated with KU Leuven and I am the author of several papers of which Jesse is also an author. The goal of knowledge base completion is to find the relationships that are missing in the knowledge base. For example, Lorenzo here, he doesn't have an affiliation yet, but you could derive that if you co-author with authors from a certain affiliation, that there's a high chance that you also have that same affiliation. You could derive this rule because both Jesse and I have co-authored on papers and we are both affiliated with the KU Leuven. Because Lorenzo also co-authors with Jesse, you may derive that he's also affiliated with the KU Leuven. Knowledge-based completion is a PU problem because all of the relationships that are already in the knowledge base are true, are positive examples, and all the relationships that are considered to be added to the knowledge base are unlabeled because we don't know yet if they belong there or not. And finally, source number 10, identification. Identification problems aim to identify examples in an unlabeled dataset that are similar to the provided positive examples. So this is clearly a positive and unlabeled data problem. Identification is often used to find new disease genes or in drug discovery where it's used to identify new chemical compounds that exhibit certain desirable properties. In the next video, I will formalize the PU learning problem by going over some important concepts like the labeling mechanism and the scenarios that we encounter in PU learning. If you want to know what those are, check out the next video.